All right, so last class we learned that most of the chemical reactions that we do or we see can be categorized into 4 classes. What are those classes? Decomposition, combination, single displacement and double displacement. And we looked at the double displacement reactions in detail. The 3 types of double displacement reactions. Those are precipitation reactions, gas formation reactions and acid-base neutralizations. Okay. Let us look at the other types of reactions also into a little bit details. So the next one we would look at is decomposition reactions. Again, as the name suggests, decomposition means a single compound breaks down to smaller compounds or its constituent elements. That's what decomposition reaction is. So here is an example, mercury oxide, which is a solid. If you heat mercury oxide, most of the decomposition reactions would happen if you heat those compounds. Okay? Heat would usually break them down. So when you heat mercury oxide, it will decompose to its constituent elements, liquid mercury and oxygen gas. That's what this test tube shows. Mercury is the only liquid metal we have, so that is showing up in the bottom of the test tube as a liquid, and then you have oxygen gas. Okay, is everybody settled down? Please come in, we start the class at 12:30, so you're supposed to be here by 12:30 and settle down, okay? So let us look at this activity. Let us predict the products and then balance the decomposition reaction. The reaction says platinum 4 chloride, the formula is given to you, decomposes to its elements. So we have the clue right there. What should be our products? So what are the elements in platinum chloride? Platinum and chlorine. Okay, so let us try to write down those elements and then balance the equation. Now, platinum is, of course, Pt, platinum. How about chlorine? Cl, but if I just write Cl, would that be good? It's forming elements, so they are going to be neutral. We are not trying to write down the ions. It would be Cl2 gas, because remember, chlorine is one of those diatomic molecules existing naturally as diatomic molecules. So it would be Cl2 gas and metal platinum solid. Let us see whether the equation is balanced or not. Is it balanced? No. What do we need to do? We need a 2 in front of Cl2. So that would be equation balanced. So that is a decomposition reaction. Platinum 4 chloride decomposes to its elements. Another decomposition reaction would be what you guys have performed in this week's lab, heating the marble chips. Okay? When you heated the marble chips, what happened? Marble chips, the formula, the chemical formula of marble chips is calcium carbonate, CaCO3 solid. When you heated that, you actually decomposed calcium carbonate to calcium oxide solid and carbon dioxide gas. So this is an example of a decomposition reaction where a compound breaks down to smaller compounds. And platinum chloride one would be an example to a compound breaks down to its elements. Both are decomposition reactions. Both require heat. Okay. Well, the answer is written, just above what I wrote. Now, the opposite of decomposition reactions are combination reactions, where two substances combine to form a single compound. So it could be two elements combined to form a compound, or two smaller compounds combined to form a larger compound. It could be both. Now, most of the metals would react with most of the non-metals and form ionic compounds. Those are all combination reactions. A metal and non-metal comes together forming an ionic compound, like sodium and chlorine, two elements, one metal, one non-metal. They will form which ionic compound? Sodium chloride. Okay. So now a non-metal may react with a more reactive non-metal and form a molecular compound, or a compound and an element may combine. So anytime when two things combine together and forms a new substance, it would be a combination reaction. So the general notation is again A plus B forming AB. Now what we are shown here is the reaction where carbon monoxide combining with oxygen and forming carbon dioxide. So that is a compound and an element may combine to form another compound, the last case. Okay. So if you look at that reaction, just showing the picture, you have carbon monoxide and oxygen, O2 gas, and the product is carbon dioxide gas. So that is an example of combination reaction. Let us predict the product of this combination reaction. It says this is a combination reaction, so that gives you the clue what should be your product. These two are going to combine together and make a compound. So it is a metal and a non-metal, so it is going to be an ionic compound. That means they are going to be formed based on the charges. So we need to identify what are the charges of each, and then they will then we will make them combine together and form the product. So aluminum will be what charge? Aluminum is 3 plus, and bromine Br is 1 minus. So when you combine these two ions, how many each you need for electrical neutrality? What happened? What? One each will not give you electrical neutrality. Aluminum is 3 plus, Br is 1 minus. You need 3 bromine or bromides for 1 aluminum, right? Electrical neutrality. We are looking for the lowest possible case. So if this is 3 plus and this is 1 minus, to balance 3 positive charges, how many negative charges you need? 3 negative charges. So that means the formula must be Al Br 3, 1 aluminum and 3 bromines. Now go ahead and balance the equation. I know where the confusion is coming from. I kept repeating this in last class. Do not do those two things together. Writing the formula and balancing. Everyone was looking at, I see only 2 bromine there, so what am I going to do with it? That is the next step, guys. That is why I keep repeating this. You might find me, why is she keep shouting on us on this point? Yes, I'll keep shouting on it until you register this. That's my intention, okay? Keep these two things separate. Identify the ions with the correct charge, then write down the formula. That time don't worry about what do I see in front of me, how many I have. That comes as the second step, which is balancing the equation. Okay? So if you have Al3 plus and Br minus, you have only one possibility for electrical neutrality, AlBr3. Now we are going to balance the equation. What is our problem? If AlBr3 is our product, what is wrong with that equation? We need, well, we see 3 bromines on the right side but only 2 on the left side, correct? We need to make those two numbers the same. I mean both sides the same. What can we do? When you have 3 and 2, what is the easiest way? Aim for 6. If I want to make 6 bromines on left side, what will I do? I will put a 3 in front of Br2. So I have 6 bromides now. How about right side? How can I get 3? I mean, how can I get 6? putting a 2 in front of AlBr3. Now I am taken care of bromines. But while doing so, aluminum's balance is disturbed. Correct? Now you have 2 aluminums on right side. We see only 1 on left side. What will you do? You will put a 2 in front of aluminum. Now the equation is balanced. So please do this as 2 separate steps. Then you will not make a mistake. If you try to combine those 2 things together and try to write down the formula, you will make a mistake. Formulas follows ionic charges, electrical neutrality. Okay? Keep saying that to yourself. So, right there. That's our answer, 2Al plus 3Br2 giving 2AlBr3. Okay, now we are going to look at single displacement reactions. And what are single displacement reactions? A free element, in this notation, A is the free element, will displace another element from a compound. So CD is the compound. So A is going to displace C and takes its place. So you have AD and then C is existing as the free element now. So only this one set of ions displacing each other. That's why we call it single displacement. Versus double displacement, both sets of ions will swap their partners. Therefore it is double displacement. So here is an example of a single displacement reaction. Copper, metallic copper, put into silver nitrate solution, forming copper nitrate solution and silver metal. So here the free element copper is displacing silver from solution. Silver nitrate is your compound, aqueous compound. And so you have copper nitrate and silver as the free element now. You will perform this reaction in lab when you do single displacement reaction lab. So this picture shows, you are not going to perform in this much large volume. You are going to do it in a small test tube, okay? But the beaker shows, well, the beaker first have silver nitrate, which is a clear solution, and you put a copper wire, okay? The copper will displace silver. So the silver will start depositing on the copper surface and copper will come into the solution and make copper nitrate solution. Copper nitrate is blue in color. That's why this solution will start turning blue. And if you look at the surface of that copper wire you put into the solution, this is what you will see. Pure silver, the shiny silver metal deposited as small tiny crystals. Now, this reaction which we looked in the beginning of this chapter when we started how to balance an equation is a single displacement reaction. Aluminum, free aluminum metal, displaces iron from iron oxide and forms aluminum oxide and iron as the free metal now. Here is another single displacement reaction. Iron displacing copper from copper oxide, forming iron oxide and copper metal. This reaction is the reason behind Statue of Liberty being closed down for renovations for a long time in '96. What happens is, Statue of Liberty, how is it made of? Copper on the outside, but the inner network is iron. Yeah, you thought it's all copper? No. Yeah, it is iron. Inner framework is of iron, but the outside is made of copper. But we see Statue of Liberty always blue in color, correct? We all know what is the color of pure copper metal. It doesn't look that way. What happens? Think about the location of Statue of Liberty. It's always in an atmosphere where the air is so moist, right? So much humidity. It's four sides surrounded by water. So what happens is, in presence of so much moisture, the pure copper will oxidize and form copper oxide. So now you can think about it. Statue of Liberty has iron inside, and now outside is copper oxide, not pure copper but copper oxide. When iron and copper, when pure metals kept together, no problem. They'll just stay as it is. They don't do any disturbance to each other. But the moment copper is turned to copper oxide, now iron is, aha, I can go and displace copper from copper oxide. So iron will start displacing copper from copper oxide and takes its place, forming iron oxide. What is iron oxide? Rust. What we call in common terms, oh, something is rusting. You know, that brownish stuff that, you know, let's say if you put a nail or something outside during the winter, and when you later find it, you see the brownish deposit on an iron, on the nail, that is rust. And you know how delicate that is. You can just, you know, give a pinch to that and it will become like powder. So it will form iron oxide, which is rust, and copper metal is going inside now. Okay? So this was the reason for the Statue of Liberty to be very weak, so they had to close it down and they had to rebuild the iron network inside. And this time when they build it, we have a lot of ways to prevent corrosion, rusting. So this time they have taken preventive measurements so that the iron will not displace copper oxide. Okay, so you will put actually, I mean it's not in here, but if anyone is wondering how do you prevent that, you would put a more active metal. We will talk about activity series of metal. All metals do not have the same reactivity. So you will put a more active metal so that iron will work with that guy, leaving copper alone. So even if you have copper oxide outside, as Statue of Liberty always has, even at present, iron will not try to do the single displacement with copper, so that the statue is intact. Okay, so we have so far seen 3 single displacement reactions. The first one is this one, where we saw copper displacing silver. Then the second one, aluminum displacing iron, and the third one, iron displacing copper. Oh, sorry, not there yet. Let us just look at this slide one more time. So that copper and silver solution, does copper displace silver or silver displace copper? Or among the two metals, which one is more active? One way of answering that question is go to the lab and do an experiment, right? Let's say we go to the lab and we do this experiment. This is what we are performing before. That is, we take a silver solution and put pure copper in one of the beakers. In another beaker we will take copper solution and put pure silver, and we will observe which one is displacing which one. Let's say we left it like that for a week, just to make sure, if anyone is thinking maybe if I give enough time something will happen. So I left it for a week. You came back on the next week's lab and you looked at both beakers, and this is what you would see. The first beaker where you had silver solution and pure copper metal put in, you see something. There is a deposit of silver on that copper metal. Look at the second beakers, compare them before and after. Do you see any change at all? No, you don't. And the second beaker had copper in solution and pure silver piece put in there. So from this observation we can conclude that silver cannot displace copper from solution, correct? If silver could displace copper, then copper should get deposited on the silver piece. But we don't see that. Whereas we see copper is displacing silver. That is why we are seeing silver getting deposited onto the copper piece. So from these 3 reactions we have observed, we can say copper is more reactive than silver, and that iron copper Statue of Liberty reaction, we can say iron is more reactive than copper. And the first reaction we have seen, aluminum and iron one, aluminum is more reactive than iron. These are the 3 observations we have made. But How can we make predictions without doing experiments? It is not possible to go to the lab and test every single metal with every single other metal solution to decide which one is more active or which one will displace which one. Correct? So we will have something called an activity series, which is a list of most of the active metals, most of the commonly used metals in the order of decreasing reactivity. So this is your activity series. I don't know which page, 185? Okay, it's in page number 185 of your book, activity series. And again, this does not list all the metals, but we will see most of the metals we encounter in lab or in day-to-day compounds. And this table is, as you can see, the arrow goes up and it says increasing activity. Meaning thereby we will find the most reactive metals on the top of the table and the least reactive metals on the bottom of the table. Okay? Now, how do we use this? Or using this table, how can you say which one will displace which one? The way we use this is any metal on the top can displace something below it from solution. That's the only way it will work. A metal can displace another metal below it on the activity series from solution. Okay? So, look at the position of copper and silver. Copper is above silver in the activity series. So, if you put copper metal into a silver solution, it will displace silver. Whereas you put silver into copper solution, you didn't see anything, correct? Because silver is below copper, so it cannot displace copper. If you look at the other examples of iron and copper, here is Fe, iron, here is copper. So iron will displace copper, but copper cannot displace iron. Similarly, what was the other one we looked at? Aluminum and iron. Aluminum is above iron. Here is iron, here is aluminum. So aluminum will displace iron from solution or from a compound. But pure iron cannot displace aluminum from a compound. Okay? So anything, so you are going to, this table you don't have to memorize. I will provide this table for you to use in the exam. So you are going to look at where is my pure metal. The pure metal can displace something below it from solution, not the other way. Keep that in mind. So, as I said, these are your least reactive metals. Just look at the least reactive metals. Who are they? Gold and platinum. Why do we use them for jewelry? Because they are the least reactive metals. You don't want, believe me, you don't want jewelry made of sodium or barium or potassium or anything. You won't be able to wear them. We want to wear something that do not react with everything, right? So that is why we have these guys in the bottom, which we use. Gold and platinum basically doesn't react with anything. You have to prepare a special, even not with concentrated acids alone. You have to prepare a special mixture of concentrated acids to dissolve gold. Otherwise, usually, they don't do anything. So let us try to answer these questions. Will magnesium displace H+? Oh, 1 second. On this table, we call it metals reactivity series, but we do see hydrogen given there. Is hydrogen a metal? It is not. So why do we give hydrogen on that series? Not hydrogen will react with metals. What happens is metals can react with acids and displace hydrogen. In acids, hydrogen will act like the metal, the positive ion, H+. Okay? So that is why hydrogen is given along with this in this table, even though it is not a metal, because metals can react with acids. So anything above H2, all these metals can react with acids and release hydrogen. Do you think any of these metals react with acids and release hydrogen? No, they do not. Okay. So, will magnesium displace H+? Yes. You have performed that in this week's lab? Didn't you put magnesium strips into 4 different acids and observed gas evolution? What gas was that? You put magnesium into acid, and how do you get carbon dioxide? H2, hydrogen gas. You put the burning splint into the mouth of the test tube and you heard popping sound, and hydrogen is the explosive gas. Carbon dioxide is something that would put out the flame, right? So that was all, as I said, that was all single displacement reactions you have performed, those 4 of them. You have put pieces of pure magnesium into 4 different acids, and all 4 were single displacement reactions. It released pure hydrogen gas. Will aluminum displace H plus? Yes, it will. Will iron displace zinc? Where is iron? Where is zinc? Here is zinc, here is iron. If I put a piece of iron into a zinc solution, do you think I will see iron displacing zinc? No, I will not, because zinc is more active than iron. Zinc is above iron, so it cannot happen. What if I change or switch the positions? That is, what if I put zinc into an iron solution? Then yes, zinc can displace iron because zinc is above iron in the activity series. Well, you are even given that reaction there, magnesium with the hydrochloric acid, forming magnesium chloride and H2 gas. Similarly, you can do all the other acids also. Everything releases hydrogen gas, and then magnesium combines with the negative ion of the acid. All right, let's have a clicker question. Have the activity series open in your book. You can refer to the activity series. Here is the question. Consider the what page is that, Sandra? 185. Thank you. So consider the equation. Nickel chloride is the solution, and I am putting pure copper into it. And I have written down a right side of the reaction. My question is, would it happen this way? Yes, no, or maybe. Use the activity series and check the positions of both metals and see who can displace who. That would tell you whether this reaction will happen or not. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Do you all have clickers today? Everyone has clickers, right? Okay. So nickel chloride is your solution or the compound, and iron is the free metal. Oh, I'm sorry, copper. Oh, we talked so much about iron that I'm sorry. Copper is the free metal, nickel chloride is the compound in solution. Can I say the activity series, please? Yeah, you have nickel. Good. I was just thinking whether nickel is given or not. Another 30 seconds, guys. That's all you need. You're not trying to write down anything. You're just looking at the activity series and just look at the positions, and that should tell you. Focus only on the left side, okay? As I said, I have written down the right side and I'm asking you guys, is it possible or not? Maybe. It's always E for Richard. Yes. Even though I don't have an E in there. I'll stop the clock at...
Well, seeing it that way is different than you just saying, will something...
displace something from solution. Yeah.
From solution?
Yeah. A free metal displacing a metal from solution. That is what is single displacement reaction. Okay. Okay. Let's see. I have all 17 in here. Let's discuss this one. Okay. You didn't answer?
No.
Then how I had seen 17? I had only 17 heads counted, right? Okay. Well, I haven't shown you guys the answer. I can start the clock for another 15 seconds and everyone can press. Please press once again. No, okay. All 17 from here?
Sure.
Okay. All right. Nickel chloride is my solution and I have pure copper metal. So if I put a piece of copper into nickel chloride solution, would something happen or not? Or copper displace nickel from solution or not? No, it will not, because I'm not saying it differently. That's what is the meaning. Okay. So a free metal displacing another metal from solution. So that's what I kept saying. The free metal should be on the top. Then only it can displace something from solution. Okay. So if copper was on top of nickel in the series, then yes, this reaction will happen. But in the activity series, where is copper? Is it above nickel or below nickel? It is below nickel. So can it displace nickel from solution? It cannot. Therefore, this reaction will not happen as shown. Well, I'm glad nobody answered maybe. What? Yeah, that's right, maybe. Uncertainty principles. So once again, guys, you will have couple of questions, not couple of, I think I have 2 or 3 questions like this in your upcoming exam. Okay, so make sure you are looking at the position of the pure metal, whether that is above or below the other metal in the solution, because displacing means what? If you put a pure metal to a solution, then only it can do some displacement. If you keep 2 pure metals, it doesn't do anything, right? So that's what you are checking. All right. Now, a 5th type of reaction, we did not put combustion reaction in the four major categories of reaction, but this is the 5th type of reaction that does not always fall into one of those 4 categories. In a combustion reaction, a substance will react with oxygen, which will produce a flame, and in a combustion reaction, your products are always carbon dioxide and water. So when you say it is a combustion reaction, there are a couple of things, even though it doesn't say explicitly, a couple of things you can assume. You need oxygen, O2 gas, as the reactant. Combustion reactions cannot happen without oxygen as one of the reagent or reactant. So that is something you should know, even though it doesn't say explicitly. Another point is, in a combustion reaction, you will have carbon dioxide and water as the products. Like in acid-base neutralization, we can always say water is one of my product. Just like that, in the combustion reaction, you will see carbon dioxide and water. So this reaction which we have given here is something that you perform every day in lab when you light a Bunsen burner. CH4, methane, natural gas, you burn that with oxygen from air, and you produce gaseous carbon dioxide and gaseous water and a flame, which you would use for, of course, heating your water or whatever you are heating. Okay? So most of the combustion reactions, or the most common combustion reaction, is the reaction that involve a hydrocarbon burning with oxygen producing carbon dioxide and water. What do we mean by hydrocarbon? Compound that contain hydrogen and carbon, as the name suggests. Petroleum compounds, most of our fuels, they are all hydrocarbons. So here is an example of octane. What is octane? The gas that we put into our cars. Octane burning with oxygen, producing carbon dioxide and water. Well, this reaction is the perfect situation. That is, if octane burns completely with oxygen, we should see only carbon dioxide and water and then lot of heat, and which is what we use in an internal combustion engine to run the car, the heat energy that is produced. Okay? But we haven't achieved this complete combustion reaction in our car engines yet. We do produce, octane doesn't burn this completely in our car engines. That is why we produce a lot of other gases also, which would pollute our atmosphere. But theoretically, this is what should happen, so that we should not be polluting our atmosphere. We should produce only water and carbon dioxide. And as I said, a lot of heat energy. So even though it doesn't say what is your reactant, what is your product, if it says a hydrocarbon, most of the time hydrocarbon means you will be given the formula, because you don't know, what are hydrocarbons. If I just say octane, you wouldn't know it is C8 and H18, correct? So most of the time it will give you the formula. But if it says it is a combustion reaction, then you should remember, okay, then oxygen, O2, is going to be my reactant, and my products are carbon dioxide and water. Then you can write that down and balance the equation. Okay, keep that in mind in combustion reactions. Okay, now we are on to the last part of this chapter, representing reactions in aqueous solutions. So we talked about the different types of reactions, and how do we actually represent reactions when they are in solution? Okay, what ions are there? How do they exchange each other? What do they form? We are going to look into those details. So when reactions occur in water, of course, the soluble ionic compounds, we know when they are dissolved, they dissociate and exist as ions. So the soluble ionic compounds exist as separate ions, not grouped together with each other as it might seem from the equation we write down. Say for example, silver nitrate aqueous and sodium chloride aqueous. Both are aqueous solutions. When we mix that, we will get silver chloride, a white precipitate, an insoluble solid, and sodium nitrate solution. Right? If you really look into this solution, say for example, you are mixing sodium chloride aqueous. Does that mean water and NaCl molecules? No, it is not. NaCl, when it is dissolved, it exists as Na plus and Cl minus ions, because it is a soluble ionic compound, and ionic compounds will dissociate into ions when they are dissolved. Similarly, silver nitrate, silver plus and NO3 minus, nitrate minus ions. Those are the two ions you will see in that solution. If you look into the beaker after the reaction is performed, the white solid is AgCl existing as solid, whereas sodium nitrate is again aqueous species. That means this is separated into Na plus and NO3 minus ions. So when we write an equation like this, showing just the formulas and physical states, and this equation is balanced as it is written, so we don't need any other coefficients. The coefficient is all 1 in front of each the formula. We call this a molecular equation, meaning thereby it is showing you the molecular formulas of the species you are reacting and the species that you are forming. Reactants and products are given using their molecular formula, that is molecular equation. Now we will have two more types of equations that we can derive from the molecular equation. Okay? Now if you write down your soluble ionic compounds as separate ions, that equation is called ionic equation. Or in other words, it is showing the species that can exist as ions. We have to write them down as ions. So the same equation you have seen before, silver nitrate aqueous means it is, as I said, Ag plus ion and NO3 minus ions separates into. Sodium chloride will separate into Na plus ion and Cl minus ion. On the right side, this is an insoluble solid, so it does not separate into ions. If it is insoluble, how can it separate into ions? When do something separate into ions? When it is soluble. Okay? Ionic compounds has to dissolve, then only they can dissociate or separate into ions. So this is not soluble, therefore we do not separate into ions. Whereas sodium nitrate is soluble, so that will separate into ions. This equation is called ionic equation. So simply from the molecular equation, whatever is aqueous, you are just splitting that into the corresponding ions. That's all you are doing for ionic equation. So insoluble compounds do not exist as ions, and the ions that exist on both sides of the equation, both sides meaning thereby left side and right side of the arrow, on the reactant side and on the product side. Ions that exist on both sides are called spectator ions. They are just there on both sides, just hanging out. Just like spectators do on a game show. They don't do much. The actual players are playing the game. But the spectators are just hanging around, having a good time and cheering up, right? That's what some of those guys also do. They don't do anything basically. They just exist on both sides, just to give others company. Let's put it that way. So in this equation, who are the spectator ions? Who would you call spectator ions in this equation? Check one by one. Who exists exactly the same as on both sides? We see Na plus and Na plus. Also NO3 minus and NO3 minus. So those two ions are spectator ions. You already just answered that question. Who are the spectator ions in the ionic equation? Note that.
If they're all soluble to begin with, how do you know which one's insoluble?
Didn't we learn about solubility table last class? We did. When we did the double displacement reaction, it is a double displacement reaction, so you would identify all the ions on left side, you will swap them, make the products, then you use the solubility table to figure out who is the insoluble species, correct? So you have to do that. We are cumulative always, guys. Don't think that we will learn something new in this class. No, we will learn something new and add it to what we did before. That's what we are doing now. So here we are assuming you know so far how to swap them, how to balance, and to figure out who is the solid. Okay? So figure out who is the solid, who is aqueous, and split all the aqueous species into the ions. That is how you get the ionic equation. Now the third type of equation, in which you will just delete or you will just neglect the spectator ions and write down what is left with. That is called net ionic equation, or actually these are the players, the Ag plus and Cl minus. Ag plus and Cl minus is actually undergoing some change, forming silver chloride solid. That's the actual result of that chemical equation. The other guys, spectator ions, as I said, they were just hanging out on both sides, not doing anything else, just hanging out. Okay? So from molecular equation we can derive ionic equation, which will show all the soluble species as ions. We do not touch the insoluble species, just because by definition insoluble species cannot exist as ions. Then we identify spectator ions, which are ions that exist on both sides. Eliminate them from the ionic equation, you will get net ionic equation. We are going to practice this because this is a sure short question in your exam. Write molecular, ionic and net ionic equation of the following reactants. Okay? So we will always get double displacement reactions for writing this type of equations. So it would kind of summarize what you have learned in this chapter. That is writing the formula, swapping the ions, writing the formula, balancing the equation, looking at the solubility table, figuring out who is solid, who is aqueous, then splitting them to get ionic equation, and eliminating spectator ions to get ionic equation. A lot of things to do, but when you do them step by step, you will see how easy that is. Shall we? Okay, let us practice. Barium sulfate used in the white pigment lithopon can be prepared by mixing solutions of barium chloride and sodium sulfate. Write balanced molecular, ionic and net ionic equation for the reaction. So read that question carefully. First identify what are the reactants. What are you mixing? Barium chloride and sodium sulfate. So those are your reactants. So we will start by writing down our reactants. Let me get a new page, and because I won't be able to write everything down on that space provided. Okay, so we said we mix what? Barium chloride.
Barium sulfate.
Yeah, sulfate.
It's barium sulfate.
We are mixing barium sulfate. Read the question again. We are mixing barium chloride. Formula of barium chloride. I wrote it down. BaCl2. Does everybody follow why is that? Why is it BaCl2? Chloride is 1 minus, barium is 2 plus. So you need BaCl2. So solutions of barium chloride, meaning thereby it is a solution, it is aqueous. Plus, who is your other reactant? What else are you mixing it with? Sodium sulfate. What is the formula? Na. Is this correct? Check for the charges and make sure they are balanced. SO4 is what charge? 2 minus. So how many sodiums you need? You need 2 sodiums. So Na2SO4. That is also aqueous because it says solutions of barium chloride and sodium sulfate. So you identified your reactants with their physical state. That is the first step. Now let us try to write down the products. As I said, it is a double displacement reaction. One of the product is given to you in the question itself. Barium sulfate. Otherwise also, even if you do the double displacement reaction, you will see barium sulfate is one of the product. What is the formula of barium sulfate? BaSO4. SO4 is 2 minus, barium is 2 plus, so I need only 1H. BaSO4, and who else could be my product? NaCl, sodium chloride. Now, One of them is a solid, one of them is aqueous. Who is solid, who is aqueous? Use the solubility table. If you stare at them, they won't tell you. You need the solubility table.
Barium sulfate is not
Barium sulfate is not
soluble.
soluble, meaning thereby it is a solid. How about sodium chloride? It is insoluble? It is soluble, meaning thereby it is aqueous. Let us balance the equation. What's wrong? As it is written, we have to have 2 chlorides on right side and 2 sodiums on right side. So placing 2 in front of NaCl will take care of both, right? This equation is called the molecular equation, which shows the formulas, physical states, and it is balanced. So this is your molecular equation. This is 95% of your work in that problem. Once you get the correct molecular equation, writing ionic equation and net ionic equation is very easy. All you need is just to look at, oh, where does that line come from? I didn't put that line, guys. Okay. Okay. Uh-oh. Now what? All right. So this is the molecular equation. Now, ionic equation is anything that is soluble in the molecular equation must be split into the ions with charges. That's all. So anything that is soluble, meaning thereby anything that is with AQ as a parenthesis, they are all soluble, right? That's what AQ means. It is dissolved in water. They should be separated to their corresponding ions. That's all you mean by ionic equation. And you will not touch a pure solid, anything that has a liquid as the physical state, like sometimes you form pure water, which will show us H2O liquid. We don't separate that, or something that is formed as a gas. You will split only species that is AQ. So let us split each of the AQ species into the corresponding ions. BaCl2, what are the ions I have there? Ba2 plus AQ, and how many? This, now we are balanced the equation, so now onwards we are going to keep the balance. How many chloride ions I have? 2 Cl minus AQ. That is how barium chloride AQ will split. Plus, split the second one please, Na2SO4 AQ, 2 Na plus AQ, and who is my negative ion there? SO4, charge is 2 minus AQ. Done with the left side, putting the arrow. Do I do anything with BaSO4 solid? No, I do not. Please do not split the solids. So I will write that as BaSO4 solid as it is. Don't touch it. Plus, what do I do with the 2 NaClAQ? I need to separate them into their ions. What are the ions there? 2 Na plus and 2 Cl minus. This is called ionic equation. See how easy that is if you have the molecular equation. You are just looking at the molecular equation, each species with AQ as the parenthesis, splitting that into ions with the correct charge and keeping the balance. Now to get the net ionic equation, we need to identify spectator ions and eliminate them. Who are the spectator ions? Ions that exist Exactly as the same species on both sides. Check that equation. Who exists on both sides? Check one by one. Let's start with the first one. Do you see Ba2 plus Aq on the right side? No, you don't. So that is not a spectator ion. How about 2Cl minus Aq? Yes, we have that on the right side also, correct? So they exist on both sides. So that is a set of spectator ion. When you identify them, somehow mark them. I would usually just round them. Okay, some people would just, like put a line across so that just to keep it clear to your mind that, okay, I have identified them. Let's keep going. Do you see 2 Na plus on both sides? Yes, you do. So that is another set of spectator ion. Next one, SO4 2 minus. Do I see SO4 2 minus on right side? No, I don't. So that is not a spectator ion. So that's it. These are the two sets of spectator ions I have. Let us write down the equation without the spectator ions. Whatever is left, that is our net ionic equation. So what are we left with now? Ba2 plus Aq plus SO4 2 minus Aq forming BaSO4 solid. That is our net ionic equation. This is the complete answer to that question. And this kind of summarizes a lot of things you have studied in this chapter and in the previous chapters. Writing formulas were from the previous chapters. Make sure you understand this process, guys. As I said, this is a short question. We will do some more practice, but make sure you understand what we are doing here. When you do it systematically, it is, one of the easiest questions actually. Once you get the molecular equation balanced, as I said, not 95 but 99% of your work is over. You need some coffee, Sandra. You know? Everyone is good with this one? Okay. So the PowerPoint is explaining exactly what we have done, identifying the reactants and their ions, possible formulas of the products, solubility rules indicating that BaSO4 is a solid, NaCl is soluble. Therefore, we have the complete balanced molecular equation. Once you get that, as you can see, all the strong electrolytes, aqueous species, we split them. So we have the ionic equation, identifying the spectator ions, Cl minus and Na plus, eliminate them, we have the net ionic equation. Let's do another one. Well, here actually we are given the molecular equation. Identify the spectator ions and write the net ionic equation from the following molecular equation. So before identifying the spectator ion, to identify spectator ions, remember we need ionic equation. So that's where we are going to start with, okay? Let's write down the ionic equation. So anything that you see with Aq must be split into the ions. So do I touch copper solid? No, I don't. It is a solid, so I don't do anything with that. Copper solid is written as it is. How about silver nitrate Aq? I need to split that into ions, okay? What are the ions in there and how many each? Once you balance the equation, keep in mind you have to follow the balance in ionic equation and net ionic equation, okay? Don't just forget the coefficients. So, what are the ions we have there? 2 Ag plus Aq and 2 NO3 minus Aq, giving us what are we having on the right side? Cu. What is the charge of Cu here? 2 plus. Good. How do we get that? Because you are looking at the negative ion, nitrate ion, which we know that it is NO3 minus, but there are 2 of them. That means copper must be 2 plus. So Cu2 plus and once again 2 NO3 minus Aq. And do I do anything with 2 Ag solid? No, I will write that as it is. So we have the ionic equation. Now we can identify the spectator ions. Who are the spectator ions? Who exist exactly as the same ions on both sides? The 2 NO3 minus Aq. Those are the only ions we see on both sides. So that is your spectator ion, NO3 minus ion. Let us remove that and then we will have the net ionic equation. So the net ionic equation is Cu solid plus 2 Ag plus Aq giving us Cu2 plus and 2 Ag solid. This one, this is Ag plus Aq. This side you have the Ag solid. So this is your net ionic equation. This is ionic equation, and this one which is given to you is the molecular equation, and we have circled the spectator ions. Questions so far? Yes. Oh, I'm sorry. I missed that. See, that Aq should be come down.
So if they're already solid, you don't do anything?
No, if something in a molecular equation, if you see anything with S, L or G, solid, liquid, gas, do not touch them. Meaning thereby do not split them. Yes, you will carry them down in the corresponding equations, but as it is, you will not split them. You can split only species that is Aq. Okay? Species that is soluble. I think we have one more equation. Once again, the molecular equation balanced is given to us. Identify the spectator ions, write the net ionic equation. So once again, we need the ionic equation first. So this is molecular equation. Let's do the ionic equation. You guys tell me. 2Na plus. Okay, when you write the ionic equation, guys, you have to show the charges. Ionic equation, that's what we call it. So we have to show the ions, okay? Not just 2Na and 2Cl. 2Na plus and 2Cl minus plus 2Ag plus, good, and do I have 2 SO4s? Just SO4 2 minus, the charge is 2 minus, giving us, I'm going to write down my products on the lower line. What are my products? How do I write them? 2Na plus Aq and SO4 2 minus Aq plus AgCl solid. That is a solid which I cannot split or touch. I will write that as it is. This is my ionic equation. Now, identify the spectator ions, please. Who are the ions that you see on both sides of the equation? We see 2 Na plus and 2 Na plus on both sides. Who else? The SO4 2 minus and SO4 2 minus on both sides. Those are the spectator ions. We have circled them. Therefore, we can write down our net ionic equation, which will be 2Cl minus plus 2Ag plus Aq, giving us 2AgCl solid. You are 100% right at this point. However, look at this equation. What can we do? Exactly. Remember, when we write an equation, we use the lowest possible coefficients to balance an equation, correct? So when you look at this one, hey, everything has 2 in front of it. So I can just eliminate those 2's and simply write down Cl minus Aq plus Ag plus Aq, giving AgCl solid as my net ionic equation. Okay? Did everybody follow this one? Let me see, do I have any more practice questions? One more. See, I have a lot of practice questions on this one because, as I said, you guys have to get this one. Another one. Why these equations are given to you like this is, you did a lot of practice on double displacement reactions and predicting product, who is a soluble one and all that, okay? That's why it's not repeating the same process. So once again, we have the balanced molecular equation with the physical states. So let's do the ionic equation. Fe 3 plus. How do I know that? There are 3 chlorides and I know chloride is 1 minus. So if there are 3 chlorides, Fe must be 3 plus. So Fe 3 plus and 3Cl minus Aq plus, who are the ions in NH4OH? Use the ionic chart if you don't know. How do they, what are the ions in there? NH4 is ammonium. What is the charge? Plus 1. So how many I have there? 3 of them. I have 3 NH4 plus ion and how many? 3 OH minus ion, the hydroxide ion. Alright, moving to the right side. Do I do anything to FeOH 3 times solid? No, I have to write that as it is because that is an insoluble species. And what happens to 3NH4Cl Aq? What are the ions? Once again, NH4 plus how many? 3 of them and 3Cl minus Aq. There is my ionic equation. Now I can clearly see who are the spectator ions. Who are the spectator ions? The 3Cl minus and the 3NH4 plus. Those are the spectator ions. I've circled them. So eliminating them will give me my net ionic equation, which would be Fe3 plus Aq and 3, oh, my O was going to be a big one. Let me make that small. 3 OH minus Aq forming Fe OH 3 solid. So once you have the balanced molecular equation, if you don't lose the balance, you don't have to balance it again. It will be balanced till the end. Okay? So that would be your net ionic equation. One clicker question. You guys know that by now, right? When do the questions show up? What are the spectator ions for the reaction? So please write the ionic equation on the sheet and then you identify the spectator ion. All I want is just the spectator ions. But in order to see the spectator ions, you have to write down your ionic equation. Do we have any more PowerPoint slides of this chapter, guys? Okay, then let's do this one and we will stop. We will start the next chapter on Tuesday. Uh-oh, I saw some printing mistake. Please read, these 3's are supposed to be in the bottom, guys. It's supposed to be NO3 minus, not NO3 minus. That was a typing error. Instead of subscript, I might have clicked superscript. I just want the identity of the ions, okay? Not even looking for how many of them also. Just who are the spectator ions. That's all I want. Sandra is making sure. Oh. Nobody left, right? All 17 are still here? Okay, okay. I know, that's why I said I'm not looking for how many. All I want is the identity of the ions, that's all. Yes, I'm not even writing down how many are there. Just the identity of the ions. Which ions, that's all, not how many. All from here?
No.
No. So who is clicking? Maybe there are 18. Did I count the heads wrong? I thought I counted twice and I could come up with only 17. Wow.
Someone's getting credit.
Okay. Let's do this one fast. 2 Ag plus Aq, 2 NO3 minus Aq, Ba2 plus Aq, 2 Cl minus Aq, giving us 2 AgCl solid and Ba2 plus Aq, bless you, so many times, so Na3 minus Aq. Now we see who are the spectator guys on both sides as well as Ba2 plus on both sides. So as I said, I'm not looking for how many, all I want is the identity. So Ba2 plus and NO3 minus are the spectator ions, which would make our answer C. All right. Okay, thank you guys. I haven't posted the homework for this one. I think I haven't. I will definitely post it today itself. Okay? So we will have a week and we will start chapter 6 on Tuesday. Your chapter 4 homework is due on Saturday. I have given you guys extra days. Okay. All right. I'm sorry, Richard. I did not bring it.
It's okay.
You are going
I was
to...
actually curious. I looked at my grade.